Hello, welcome to another video on gPROMS. Today, we want to see how we can simulate a batch reactor in which a single reaction occurs according to this equation, A plus B goes to C, and the reaction is second order kinetics, and the reaction rate is given by this, R equals KCACB, and the rate constant, the value of the rate constant is this. Okay, we have some parameters here for each component, the initial mole, the molecular weight, the density, and the stoichiometric coefficient. So what we want to do is that we want to plot the concentration of all components and volume as a function of time. Okay, so how do we do this in gPROMS? Then the first, we're given the model equations. So we have the model equations as this. So we have the mole balance, the volume equation, the concentration equation, and the rate equation. So we have 4 equations. So we need to first do a degree of freedom analysis to see if we need some specifications before we can solve it. Now, for the first equation, so we need to count how many variables. So we count the number of variables because this is not just one equation, it's for each component. So D and I, where I represent the components. So this is Ni, so it means that, and then this is V in the equation, and this is R. So the stoichiometric coefficient nu is a parameter. So this is the stoichiometric coefficient, so it's a parameter. So we are not counting it. So we are only counting the variables. So we have Ni, V, and R. So that means, and how many equations do we have? NC equation. So which means this equation is basically 3, not 1, because we will write it for 1 for A, for B, and C. Basically D, N, A, the T. So we'll do that D, N, B, the T, and D, N, C, the T. And depending on the stoichiometric coefficient of that component, so we write the equation. This equation will be expanded in gPROMS, basically. So we have as many components as this equation. NC equation, but the number of variables is NC plus 1 plus 1. So that's NC plus 2. Then for the second equation, so V has already been counted, so we don't have any new variable here. So we're only looking at new variables. So V has been counted here, so N has been counted here. Molecular weight is a parameter, density is a parameter. So we have one equation, no new variable, so no new variable. For the third equation, Ci is new, so because it has not appeared here, so Ci, so how many equations? We have NC equation. So because remember there's a subscript here, it means this concentration will be calculated for A, for B, and for C. So that's why it's NC. NC is 3 in this problem. Okay, so basically 3 equations and 3 variables. So then for the fourth one, rate, R has been counted here. So we don't have any new C and CB have been counted here as well, because this CI is basically CA, CB, and CC. So how many equations? 1 equation, but no new variable. So if you add everything together, you have 2NC plus 2 for the number of equations. And for the number of variables, we also have 2NC plus 2. So we do the degrees of freedom analysis, number of variables by the number of equations, we get 0. So good, we can solve it. Now let's go to gPROMS to solve this problem. Okay, I already created the model. So we have the variable types. These are the variable types that we need. Then the model, here I have the parameters, the number of components. Remember the NC in the problem, the number of components. Then the kinetic parameter K, the stoichiometric coefficient was declared as an array. Remember it was new I. So that means it has an array of number of components. So molecular weight I as well, array of number of components, density I as well in the equation. Then as an array of number of components. Whenever you have subscript for the parameter or for the variable, it has to be declared as an array. Subscript I or J, it has to be declared as an array. For the variable as well, Ni, remember there was Ni, so an array of number of components, volume, rate, and concentration. So these are declared. Then the first equation, so it's written the mole balance equation, d Ni dt equals volume times stoichiometric coefficient I times the rate. So that's the mole balance equation. Then the volume is sigma, it's just one equation. So sigma n1 to number of components. So times molecular weight 1 to the number of components, divided by density 1 to the number of components. Okay, so we need to do this because we are doing, sigma is operating on them. So it's going to sum whatever it gets for each volume. So sigma needs to operate on an array. So we cannot use a for loop here. So we need to do n and specify how we want to do the summation, like how from where to where. So here we want to start from the first component to all the components that we have. So that's why I've used one up to number of components. If you leave this open in gPROMS, if you don't specify anything, you just put the parentheses, it will still work. Okay? You can remove this and leave the parentheses, so you can have molecular weight, parentheses, density, parentheses, and end parentheses. gPROMS will expand it for all the components. I just like to be descriptive, so I recommend put that so that it's explicit. We know we are going from one to number of components. Then the concentration, we need a for loop here because we need to write that for each component. Anytime you need to write a number of equations, if it's not just one, if the differential variable, that is the variable that has the d, the t, if it is an array, if it is not just one, then you need a for loop to write for each of the components in this case. So the same thing here, we need a for loop because the C that we have on the left-hand side is an array. So we need to write it 3 times. That's why we need a for loop that goes from 1 up to 3, the number of components that we have, A, B, and C. Okay. Now to the process, I have simulate BR1. That's what I've called the process. I've set the parameters here. So the first thing to do is to create a copy of the model. I call it T101 as BR1. BR1 is the model name, and set the parameters. So this is the number of components. This is the stoichiometric coefficient, molecular weight density, and then the kinetic rate constant. Then the initial condition, remember there are 3 differential equations. So we need to specify the initial condition for the n. Remember we have one d and I dt, so that's the only differential equation. It is not just one, it is NC differential equation. So basically 3. So that's why you need to specify the initial condition for each of them. So for the initial mole of A, the initial mole of B, and the initial mole of C. A is 1 in that array because A comes first, B is 2, and C is 3. That's why I've done it that way. Okay. Then here I specify the solution parameter. Under solution parameters, the reporting interval. So I want to get the result after every second. Then schedule. Run the simulation for 1,800 seconds. Okay, so if we run it, and you already have the reporting interval captured here, then we have the solution. To expand that result trajectory, so I can plot the concentration. So if you click that, then and graph, so you can see the concentration of A and B, which are reactants, they decay, they go down, and the concentration of the product, which is C, is increasing. Okay. Then for the volume as well, so the volume of the reactor is going down as well. So and it remains constant around after like 800 seconds. Okay, so that will be it for this video. I hope you find this useful. If you are new to this channel, don't forget to subscribe and hit the notification button so that you can get notified of my new videos. Thank you very much for watching, and I will see you in the next video. Bye-bye.